Okay, new chapter. It's a Friday. Yeah. So we're in thermodynamics, but a lot of what we're talking about almost looks like kinetics, but it's not. What's the difference, I don't know, anybody, between thermodynamics and kinetics?
Thermodynamics has to do with heat.
Has to do with heat. Well, kinetics could have to do with heat too. Things could slow down or speed up with heat. I kind of gave you a hint there.
Thermodynamics is the speeding up or slowing down of molecules.
Kinetics is all about like that movement, like that darn ball bouncing. That's why I'm describing this, because I see a ball bouncing on a table. I'm thinking of kinetics, right? Because it's movement. It's things moving from here to there. They're progressing over time. Is a factor. Is time a factor in thermodynamics? No, there is no time. All there is will it happen? Will it not happen? Will it happen more likely? Will it not happen more likely? You know, in other words, they don't like to use that. They like to use the word spontaneous and spontaneity. What's the degree of spontaneity? What's the environment? What are the qualities? What helps a process be more spontaneous? This has nothing to do with time. Nothing. Okay? So one thing so again, this is thermodynamics, spontaneous change. This is always true. For spontaneous changes, a natural process, energy is always dispersed into a more disordered form. And I like to think of the idea of, I don't know if I talked about this or not with you. Is there energy in the ocean? Is there an energy content in our ocean? And I mean, is there energy that could be sucked up? Sure, I mean, it's because if you suck out that energy, it turns into a solid, right? So there's a ship. Well, there may not be, there isn't one right now, but you became the president of the United Arab Emirates, and you want to save the world, so you want to develop all this power, this engine that's going to suck energy out of the ocean, right? Think of it on the back of a ship. It's sucking energy out of the ocean and just shoots out ice cubes out the back, right? Sounds like a good idea. Because that's going to hurt the greenhouse effect, right? Might even help cool things down a little bit. No impact on the environment, right? That stuff is just going to melt, but the ship gets to go. So apply that engine to a whole bunch of different things. Now, would it be worth putting money and effort and energy into that? That's where thermodynamics comes in. It tells you what questions are possible, what things are not possible. That is impossible. And there will be a better insight into it later on in about 20 minutes from now. But that's the second law of thermodynamics. It just won't work. Right? That you need energy there's kind of an insight into that sentence. Right? If you take heat, suck it out of the ocean, and shoot ice cubes out the back, is energy getting into a more dispersed form or a more ordered form? You're shooting out ice cubes out the back. You started with liquid water. Things are getting more ordered. That takes work. That takes energy to do that. You're not going to get energy out of that. So, because mathematically it makes sense. Joules and joules, right? It should make sense mathematically. But thermodynamically, no. The second law of thermodynamics says don't even waste a penny on that kind of research. So here's a steel ball bouncing. Is it a natural process, Shelby, for that ball to bounce like that and just keep bouncing lower and lower and lower? Mm-hmm. Yeah. So that means energy, Eric, must be being dispersed into a more disordered form. Where is that occurring?
Heat when the ball hits the ground.
Yeah, there you go. Heat. Random motion when the ball hits. Okay. So we're starting to talk about dispersal and energy dispersal, so it's a nice lead-in into entropy. And we've got our the system, right? It could be our gas, our vessel, or whatever. Then you have everything that's surrounding our surroundings. So the total change in entropy is a change in entropy of the surroundings plus a change in entropy of the system. And it's always greater than 0. That delta S total is always greater than 0 for any irreversible spontaneous change. Okay. So blowing something up, right? The total change in entropy is always bigger than 0. So we're going to have a lot of problems where what's the change in entropy? And they're really talking about the change in entropy of our system. And they want to know, what is that change in entropy going to be? A lot of the homework is going to involve that. And it all starts right here. This is the definition. The heat, right? Q is heat. Transferred under what conditions? The rev probably stands for what? Reversible. So this heat transferred under reversible conditions at some temperature. And then that's that infinitesimal heat transfer at that temperature. That's how you're going to be calculating entropy. Then there can be different conditions. We're going to expand under constant pressure. We're going to have, we did the concept preview. There it is. We have a bunch of expressions to get that, okay? To get that delta S system. And that's the concept preview that we did. So before we start doing our homework, we'll probably hand those back so that you can write those expressions in. Whoop. Where is it at? Here it is. All right, here's our equation sheet. So before we start doing homework, we better write our expressions in there. Remember, you can, and you go ahead and use them straightforward. It's just that you have to be able to derive them. Okay. So we'll do that before we start doing our homework. Okay. Where are we? Now, don't forget though. I mean, the homework could be, they could tell you what the heat exchanged is under reversible conditions. Then you just divide the two, and you could get the change in entropy that way too. You're not always going to be using those expressions. And then for any process performed in a reversible fashion, the total change in entropy is always 0. So whenever you do a reversible process, delta S total is always 0. And we skipped this. We skipped adiabatic talk.
Wait, what did you say? Delta S total is always equal to 0?
Yeah, I kind of skipped. I jumped way down to here. When you do a reversible process, delta S total is always 0.
Gotcha.
But I skipped our adiabatic talks. We better go back. So if it's adiabatic, they say the change in entropies of the surroundings is 0. Does that make sense? Yeah, because Q is 0. And so yeah, if heat can't be exchanged between the system and the surroundings, there can't be any Q. And that's what they're trying to say here. So since Q surroundings is 0, delta S surroundings is 0. Okay. So for any adiabatic process, that'll work. So I don't know. This Carnot cycle is kind of, it's hard to see. That's why I brought a little tool here. But they use it to show that entropy is a state function. But it's kind of hard to see. And it just consists of starting at one point and ending up there again. Okay, so they do isothermal expansion, this piston's going out, and adiabatic expansion, isothermal compression, just all these different processes to end up back at the same point. So there's no change in entropy. So it's a theoretical idea, but there's some insight into it. And what I wanted to get into is this efficiency idea, that all engines have an efficiency. And you can take the work so when you to have an engine, you pretty much need a cold sink, is what this is trying to say. So you have a cold sink and a hot source. So it's kind of like if you had your car engine going, right? That's definitely an engine. And if you could make the borders of it somehow a lot colder and let that heat escape a lot easier, you're going to really increase the efficiency. You're going to really increase the miles per gallon on your vehicle. So every engine needs a hot source. It's kind of, well, hot source is where it's starting, but every engine needs a cold sink is where it kind of makes a little more sense to me. It needs a place for that heat to escape to. And it's kind of leading back up into this idea, because engines are supposed to be, if it's not spontaneous, it's not going to be an engine. You're not going to be able to do any work. So energy to be dispersed into more disordered form, you need that cold sink. So the hot sink, the hot source is supplying heat, QH, right? The cold sink is removing heat. So this difference between what's being supplied by the hot source and what's going to the cold sink, there's your work. That's how much work you can get out of it. Now, it might be easier if I show you this. This is the first time I've brought this out, so I've been playing around with it. And what it's called is called a Stirling Engine. And I forgot one of them. Hang on, I got to go get it. So what guys at MIT did at a very, well, you don't have to think of the MIT story. You can think of, okay, you've got those turbines that are blown in the wind, generate electricity. You've got solar cells, generate electricity. Well, you have a Stirling engine generate electricity. What it is you have, actually they have these big lenses and they shine down on this part of the Stirling engine. So this part gets hot. This part is your cold sink. And then, there's a lot of moving parts here, but the idea is when this gets hot, right, the air expands and pushes the piston up, right, pushes the piston up. And then the air is going to cool here, allows the piston to fall back down. So it's just, right, the heat is pushing the piston up, it cools, piston falls back down again, right? If you can just make this hot enough and keep this cold enough. And there's some guys at MIT that developed, so I was trying to build this thing to show you guys this stuff, and I got it to work by putting it on a really, really, really hot plate. But then it damaged it because it was so hot. So then I just broke down and bought one. Okay, so I'll show you how this works. But what I wanted to tell you is that, like the heat on here, there's heat that's coming off. Well, maybe it is hot enough I could get it to work. That's kind of is. It's not very, it might work. Put it over here. All right. See if I get it. See, I don't think it might not be hot enough to keep it going, because the bottom part has to warm up. And then what happens is it's going. It's working. Right? It's not dying on us. So, but this isn't very hot at all, but it's pretty warm. So it's enough to warm up the air so that it expands, pushes the piston up. It cools when it comes up here. So you have a cold source, hot source. If I can make the cold source even colder, it becomes more efficient. So how can I make it colder? All right. Cold? Does it feel cold?
Kinda, yeah.
But see, the metal has to cool down, so it takes a little while. But the can is cold. That might work better. But it seems like it's definitely spinning faster now.
Yeah, like it's picking up.
So the thinking here is, I mean, what if you could build a gazillion of these miniature Stirling engines, right? And they're all lined up on computer screens, on this thing, engines, wherever. So they can use this wasted heat. Now, there's still, efficiency still isn't 100%. And you can calculate what the efficiency is using the Carnot efficiency equation. But at least we're not wasting as much as we were before. Okay. So, but there's a lot of moving parts here, and that's kind of the negative of it. Why is something spinning? How can that generate electricity? How do you generate current with something spinning? Right? I mean, you can see there's work being done here, but it's not very useful to turn a little wheel. Right? It'd be much more useful to turn the surround this.
Is it like friction?
You guys don't remember your physics, right? How can I create electricity? I can move a what? Move a starts with an M. A magnet. Right? So have you have a just like look at a if you've ever looked closely at a engine. A little electric motor in the vacuum cleaner, right? All you can see a lot of copper wires and things in there, but they're all surrounding magnets. So there's other magnets on this turbine. So this thing spins, right? So you have magnets that are moving. It generates current. It induces a magnetic field, induces you'd have to read Gauss's law. Do you remember your physics? Anyway, so you can think of it this way. Down at the very bottom, you can induce current by just moving a magnet. Okay, just take a magnet, move it. By another magnet, you can induce electricity. So that's what you'd have here. You just have it hooked up to some little arm with the magnets on them, surrounded by more magnets, spin it, you just have current. That's how they generate AC current. Okay. So if I take it off of there and put it here, where the temperature is pretty much the same, right? Once the temperature of this guy reaches that, it should stop. It's really going pretty good. But remember, this guy is a hot plate, so you got to wait for that hot plate to cool down. It takes a while for metal to cool down. So it's very distracting. But let's see how long it takes to stop there. Okay, so Alyssa, don't stare at it. Oh, I was going to do this. That's what this was for, right? 33, the top had better be what? Better be colder. 22, right? So I should have measured it before I did this, right? How can you be scared of this? It's just air. Well, it's not really air. It's.
So I get sick, I know who to come to.
Right. Shoot, I should have done this first. What's the can? Yeah, the can's 17. Man, Padawan missed the coolest demonstration ever. Okay. So I think this is our lab that involved that tube that blew out hot air on one end, cold air on the other end. What was that called? Rank-Hilsch. And I think I dropped it and I broke it. So that's our Rank-Hilsch lab. And we may not be able to get to do it if I can't get it to work. So that's fine. Then we can just have room for one more exam, right? Okay. So yeah, don't worry about it. But that's the insight into tornadoes, right? Okay. Clausius. So anyway, there always has to be a cold sink. So that's another way of saying the second law of thermodynamics. Always has to be a cold sink. And the colder, the better, right? Colder, the better. Do you see why the colder, the better? Because if you make Tc really cold, that's going to be a really small number. Divide by Th, a much bigger number. 1 minus, really, the smaller that number is, the closer it is to 1. So 1 is the best efficiency you can get.
Wait, I have a question.
Yes.
Okay, so I know we draw.
Ooh, look at the wheel. Right? It's dying on you. Uh-huh.
So I know we draw these arrows. I know the QC's from, there's the QH and QC are on here. But what does the W stand for?
So the W, looking at it mathematically, it's the sum of these two. That's the maximum work that you can get out of this. That's the maximum theoretical work, according to thermodynamics, that you can get out of it. So that's why your engine, doesn't matter what the engine is. If you make things colder around it, allow that heat to dissipate, the engine's going to work much more efficiently, right? Because that's the maximum work they can get out of it. Okay. So that goes for anything, not just perfect gases. This is for anything. So if you keep asking if you see a question in here. So spontaneous changes, the change in entropy has to be greater than 0 or equals. Remember, it can be equals if it's reversible. Okay. What are some reversible processes that you could actually see in the lab?
Transition.
Phase transitions. Yeah, that'll be in the homework. Entropy changes accompanying specific processes. Yeah, there it is right there. Right? Solid, liquid, gas. Right? As you go up, would delta S, would the change in entropy be positive or negative as you go up that scale?
Positive.
Positive. Yeah. All right, you're getting more and more disorder. Think of it that way. More and more states. You also have a positive entropy of the transition, right? Positive delta H as you go up. Okay. And here's a bunch of our, see, they even have change in entropy of vaporization, right? Enthalpy of vaporization. Troughton's rule. All gases provide the same change in entropy upon vaporization. It may not be exact, but it is really, really close. What was that number? It's around 85 joules per Kelvin mole. Okay. So just to play around with this a little bit, if you're doing these transitions, it's reversible. So delta S with what subscript 0? Delta S total, big tot. That means delta S system doesn't quite equal delta S surroundings. They're going to be minus of each other, right? Because the system of surroundings has to be the total. So that's playing around with it a little bit. So I think we're supposed to stop here. Yeah. Oh, entropy changes, specific processes. You already kind of mentioned that. That's that concept preview. So let's go ahead and work some of these problems here. All right, did we add 7 and 8? Yeah, 7 and 8 right there. Oh, I wanted to hand this out. This is the equation sheet from from exam 3. Because you're going to need it. The equation sheet that I gave you at the end of the chapter. All right. So our equation sheet is really a lot longer than, where'd it go? Than this, right? It's really this and exam 3's equation sheet, so it's getting long. So let's start. That's why I give you these sheets, so I don't have to answer your question. If it's not on here,
Well, it's going to get long by like the ninth test.
yeah. Where's my writing utensil? Here it is. Okay. Calculate the change in entropy. When 25 kilojoules of energy is transferred reversibly and isothermally as heat to a large block of iron at 0 degrees Celsius, what expression should you use? Looking at our 2 equation sheets here we have to mess with.
We're doing 4-1?
Yeah, number 1. We have 2 sheets to look at here, Alyssa. Which one should we mess with?
You think so?
Hey, now you can stop staring at it.
Well, wouldn't we use the newer one? Because we're doing change in entropy?
Yeah. They know that 25 kilojoules of energy, that's probably what symbol?
Q.
Q. And we can even be more specific. It's transferred reversibly. So Q with a little subscript, rev. That's a big hint. There you go, over T. Because I think it looked like this, didn't it? DS was Q rev over T. Isn't that it? dq rev over T. Sorry. So delta S Q rev over T. No integrating necessary, right? They told us the temperatures, they told us Q rev, just straight plug and chug. So it's going to be what over what? Joules over Kelvin or kilojoules over Kelvin, whatever works. Okay. Make sense? Let's go on to 2 then. Calculate the molar entropy at constant volume, sample of neon at 500 Kelvin, given that it is 154.84 joules per Kelvin mole at 298. Now, the hint to me to solving this thing is given that it is at 298. So when we do this sort of thing from that concept preview, didn't we have, and we always just wrote that integral and we stopped. Really, there's what limits here? What should we really be writing here and here? Like S1 and S2 or something, right? But we never really did. We should have. We really should have, because it would have offered us insight into solving this one. Because they want the molar entropy They want S2 or S1. It will be S2 if you call this T2, right? So it doesn't really matter. It could be S1, but you got to call that T1. So we call that T2, so we have to find S2. We have to find S2. So when we went and we're working on this in our concept review, do you remember what we did? What was the next step here? This was just S2 minus S1, right? But the other side,
We did that one called T2, T1.
yeah. But we should probably substitute in for our TQ first.
Yeah, NCVM DT.
Yeah.
Over T.
I shouldn't erase, right? Let's just. Right, that's where, and this is where it makes the most sense to put in your t limits, because now we didn't have a dt here, right? There's no dt here. So it doesn't make sense to put in those t limits until you actually are differentiating over t. And they want molar entropy, so we could probably just erase what little symbol we wrote. Yeah, I could erase the little n because they want the answer in molar. Okay. So probably do what next?
Maybe
Yeah, that's. They're expecting you to look up what? CVM. So let me look it up for you. They don't give you the tables. The table only gives you CPM. Yeah, okay, so from the table.
CPM minus R.
Yeah. CPM for neon is 20.786. Joules per Kelvin mole. So, can you remember R is what plus?
8.314.
Yeah, 8.314. CPM minus CVM. Yeah, because remember that's why we needed this sheet back again. Because remember R is CPM minus CVM. Right. So get your CVM. And right, you got to use the right R. The R with joules in it. And then I think Alyssa told us, she said that to integrate that, you're going to end up with a natural log of t evaluated from T1 to T2. So you have numbers for everything. You just got to solve for this guy. Okay.
You see that ln T2 over T1, ln P1 over P2, ln V1 over V2 a lot. Look at that. It just comes out to the log of these equations.
Yeah, yeah. Except, I don't know, yeah, it does, doesn't it? Okay, so you can get a number for that. Let's see, let's check out number 3. Yeah. And say it so everyone knows what you're talking about.
Delta S equals MR ln P1 over P1.
Yes. It was P what over P what? P1 over P2. Yeah, not P2 over P1. Yeah. Pretty much, right?
No, it's constant pressure.
Oh, is it?
Oh, no,
That's not the right. It's heated under constant pressure. That's under. That was for isothermal. That's isothermal. Yeah, so not that one. It's going to be.
The NCPM ln T2 over
That's it. Yeah. Right. Maybe you can heating under constant pressure. Okay. So you know what CVM is. So you need to get your CPM. They told you what N was. They told you the temperatures. Just make sure the temperatures are in Kelvin. Right? Good? Number 4. So we don't have a concept review expression that's going to handle this. But entropy is a what function? State function. So does the path matter, Shelby? No. All that matters is initial and final states. So we can get there however we want. So let's use what we know from our concept preview and write a couple steps to get there. Right? So we're starting at 25 degrees Celsius and 1.5 atmospheres. So why don't we do some, I don't know, constant, keep the temperature constant, right? And isothermal, and let the pressure go up to from 1, you know what I'm saying? Isothermal compression. So we'll do the, I just want you to see this. We'll go from 25 degrees Celsius, right? We're at 25 degrees Celsius. And our P is going to go from 1.5 atmospheres all the way to 7 atmospheres. Okay, so now we're at 7 atmospheres, but we're at the wrong temperature. So now we have to do what? Constant pressure. Constant pressure heating. Constant pressure heating. So we're going to be at 7 atmospheres, right? Our T1 would be 25 degrees Celsius, and our T2 is going to be, what is it? 135. Oh, thank you, 135. Okay, so if you wanted to write it mathematically, I guess you could say delta S is going to be delta S step 1 plus delta S step 2. So taking advantage of entropy being a state function, we can use those concept preview relations to pretty much do whatever we want, right? Multiple steps. So for our step 1, isothermal.
So we use the equation as
Yeah. Isothermal expansion or compression. Exactly. We'll use that one first. She said NR ln P1 over P2. And then for step 2, that has to be a constant pressure heating. That's that first one again. All right? Yeah. Okay? So everybody see how to do this? We're okay? Shelby, you okay with this? So you just got to plug everything in and we'll have it. Kelly, you okay with this?
How did you
Did
know
we lose
to
you?
do like isothermal?
I just made it up because I figure there's probably got to be more than one way to do this. I don't know, would there be? Because maybe not, because with what we have, you have initial and final pressures, initial and final temperatures. The only thing you could change is the order. Do step 2 first, or no, you couldn't do that. So maybe there are a couple different answers here, but they're all gonna get the same one. So what I gotta do is I gotta keep track. That's why I write all this stuff down, so I don't lose where I'm at.
You just look for it in the equations and see how you can.
Yeah, so I know that I'm at this pressure and this temperature. I want to get to this pressure and this temperature. So first I'm going to keep the pressure constant, or first I'm going to keep the temperature constant.
Yeah.
I just want to end up at
You're just
here.
calculating the delta S's for each.
Just calculating the delta S for each component.
Individually, yeah.
So I want to write a couple steps, starting here, start, and then stop when I get there, with hopefully the fewest steps possible, the least to calculate. Okay. So I just make up some steps. Number 5. Reversibly and adiabatically they want Q. Oh, they want all of these. Q, W, delta U, delta H, and delta S. Are there any easy ones?
Q
Delta
equals
S has to be what?
0, Q is 0.
It's adiabatic.
So delta S and Q have to be 0. Yeah, Q reversible over whatever is going to be 0.
All right. I think there's one more easy one. And that's why, honestly, that's why I handed this out, because I couldn't remember the equation.
Delta U equal W?
Yeah, delta U is going to be W. Well, let's do this so no one gets lost, right? Delta U is going to be my W.
Delta U equals 0, right? Because it's
No.
infinitesimal.
Is the temperature changing?
Yes.
So delta U is definitely not 0.
Okay, yeah.
I guess adiabatic. What little special equation can you use for adiabatic for what we're looking for?
Q equals negative W, is that it?
No, it's the CPM over CPM.
Oh, that doesn't even work for this one.
Look on here. There's one more easy one. For adiabatic, you can get what? NCVM delta T is what? W. That's my work.
Yeah.
Adiabatic work. So we have W2 now. Now we have delta U because someone's noticed delta U is going to be Q plus W. So we've got all of these. What's left? Delta H. Okay. How is delta H, how is enthalpy defined? Do you remember? It's, where should be on here?
As I do back define.
How
Would
is,
it be that delta S over delta H over T? No, because that's for transition.
it's on here actually. It's a definition. Enthalpy,
H equals
what,
U plus Q?
what makes enthalpy hard, yeah, that works. That's a definition, but that's not going to help us really. What makes enthalpy hard, I think, for me, is that it's defined. It doesn't even seem to fit. I mean, pressure is changing, so enthalpy doesn't even make sense. But that's how enthalpy is defined. So you can calculate it, even though it doesn't really make a whole lot of sense. So you have to go by the definition.
So it's delta H
NCPM delta T. And it's just a definition. So that means this works always. It's a definition. It's always true. It's just how it's defined. It's kind of like, I was looking for this actually. I thought that's what I had in my equation sheet. Q with a little p on it. Because that's what enthalpy is, heat transfer under constant pressure conditions. But I don't have that on here, so don't worry about that. But inside my head, that's what it is. It's heat transfer under constant pressure conditions. So how do you get it? You multiply, get the constant pressure heat capacity times the change in temperature. That's how you get QP, even though that doesn't even exist in our equation sheet. Okay, so we know N, we know CPM. Well, we know CVM. You can get CPM. Okay, so we know them all now, right? Done. Man, you guys aren't going to have any homework left. Fly, Alyssa, fly. Number 6. Number 6. Oh, that's another one. Okay. You tell me what the steps are. Make sure you can, then I know that you're following this.
Do the.
Oh, it would be like the last one, so we could do the step 1, step 2.
Yeah, so what would you write?
Step 1, we would
The
want to
change
do.
in temperature, isothermal.
Okay, she wants to do,
No,
Shelby wants to heat first.
Heated or cooled under constant volume.
Heat under constant,
Volume.
it's heat under constant volume. Okay, so I would write those down. So heat, that means, well, T1 is 300 Kelvin. T2 is 600 Kelvin. And my volume is 30 liters. Okay. And then step 2 would be,
And then our LNV2 would be
yeah, but how would you describe the step?
Isothermal under, when we know final and initial volume.
Isothermal
Expansion.
expansion, because you're going to 50 liters. Isothermal expansion. So I would be able to describe these steps. See, without just jumping right to the equation, be able to describe the steps. Because this is perfect for concept questions, right, on exams. So be able to describe those steps. Right, Gloriana? Earn your way to the top. You really got to get getting sick of me for saying that.
Would it be a 300?
Isothermal expansion. Oh yeah, so it's going to be at 600 Kelvin. We're going to go from V1 equals 30 liters to V2, which is 50 liters. So then you just add the 2 up.
So we keep our concept.
I would grab your concept preview and just scribble down those expressions. and then hand them back to me,
I took a picture of it.
or take a picture of them or something, right? So yeah, we're out of time.